the stability of different intermediates and the application of whatever we have learned till now regarding the stable regarding the electronic effects. Okay, regarding the electronic effects. So just to revise and just to start again, if we talk about intermediates, then we have in any reactions there is a substrate that is particularly organic. This is always an organic compound. It's an organic molecule. Then there is a reagent, and this reagent, it can be inorganic. Most of the times it is an organic compound, or it can also be an organic compound but with a high electron density. Okay, that means very polar organic compound. You can say polar, other very polar organic compound or molecule. So much so that it can also have some partial charges and sometimes even a complete charge. Then substrate and reagent, they interact with each other and they first of all form an intermediate. Then this intermediate, it transforms to, now this intermediate is a charged species, or I can say that it will be an electron poor or an electron rich species. That means I can categorize this into 3 types that we need to focus on. There can be other types of intermediates too, but we mainly need to focus on carbocation, carbanion, and carbon free radical, right? And in these 3 intermediates, wait a second, just turn off my flux. Yeah. So in these 3 intermediates, the carbanion is the one which has high electron density. The other, that is a carbocation, it is electronic poor, and this carbon free radical, it is also poor in electron because it only has 7 electron, and to have a stable system we need at least 8 electron. The octet should be complete for the second period elements, and carbon is a second period element, and further on they will make product. Now before going to product, we need to understand the intermediates and why is the stability important. The stability of an intermediate is important because if the intermediate is going to be stable, that means we can easily move from this stage of reaction to intermediate, and then from intermediate to product is an easy process. From intermediate to product is an easy process because you can see here we have an organic molecule, here also we have molecule, but here we have ions kind of thing, right? So it is difficult to go from a neutral species to intermediate, that is a charged species, right? I can say that it is charged species. So this step is very difficult. So the easiness or the ease of achieving a charged species that is an intermediate will be very crucial in determining the rate of reactions, how fast a particular reaction is going on. And that is the whole concept of intermediates. And why do we study intermediates? Because we want to know which of the substrate is going to give a better intermediate, a more stable intermediate, and how fast are we going to form products. Okay, so first of all we'll learn about the carbocation. So you can write the topic. I hope the review is clear for all of you and why we are going to study the carbocation and carbon free radical and as well as carbanion. Yes or no, guys? Tell me.
Yes, sir.
Yes, okay. This is carbocation. And this is the most important, intermediate, and it is important because it will be very frequent. You will be getting carbocation very frequently. And the reason you can derive if you look at and have a look at the functional group and the substituent of carbon. So if I look at the functional group and the substituents of carbon, I will always see that this is carbon, it is attached to OH, or the carbon is attached to nitrogen, or the carbon is attached to oxygen with a double bond, or the carbon is attached to what else? It is attached to sometimes nitrogen and oxygen. What else is there? It will be attached to. So mainly these are the things that it is going to be attached to in different ways, obviously, because we know that this carbonyl group, it is very common in carboxylic acid to aldehyde and ketones, and in between there are esters, amides, oil halides, and etc. Different things. In all of these cases, you can see that carbon is attached to a more electronegative element, and it is very obvious if the bond is going to break, if these bonds are going to break, then carbon is the one who is going to lose electron, and it is going to form a carbocation. So the carbocation is important because it is very frequent, and we can easily get a carbocation, since most of the organic molecules, they are attached, they are such that the carbon is attached to a more electronegative element. So the first point that you have to remember is that what is a carbocation? This is a carbon with 3 bonds, and there is a positive charge. There is a positive charge on the carbon, and this is the structure of carbocation. Now these bonds, they can be attached to hydrogen or different alkyl groups also, or some different groups also. We we don't need to specify which groups. If you see a carbon with a positive charge and 3 bonds, that is a carbocation. And if has only 3 bonds, that means there are 6 electrons, and then I can say that it is electron poor species. It is electron poor species. So if it is electron poor species, that means what things will stabilize? So we can say electron donating groups, right? Because it is electron poor. So wherever you have poor and you have to make stability, you have to give some donors to that particular carbon chain or to that society also. If there are more poors, then you need more donors. So electron donor groups, electron donating groups stabilizes carbocation. Stabilizes carbocation. Furthermore, I can say that if you get electron withdrawing groups, right? Those people who will make the poor poorer, right? It is going to make the poor poorer because it is poor in terms of electron and electron withdrawing groups. It will abstract those electrons also. That means what we are doing, we are making someone who is poor, we are making him poorer, and hence electron withdrawing group destabilizes carbocation. Okay, now electron donating group stabilizes carbocation. That means we are talking about plus I groups, they are electron donating, and we are talking about the plus M group. Okay, so plus I groups and plus M groups. This is very important that you have to differentiate between the groups and the phenomena. So you have plus I and plus M groups, and these are minus I and minus M groups, right? Minus M groups. Now, furthermore, and we have generalized this point that wherever you have charge, and if there is a delocalization of charge, right? Delocalization of charge, or there is a spreading of charge. So if the charge is delocalized, that means that species, that molecule is going to be stable. So we can say charge delocalization. Charge density should decrease, so charge delocalization makes the carbocation more stable. Makes the carbocation more stable. Okay, so what does this mean? So there are two phenomena which are responsible for charge delocalization. Okay, which are responsible for charge delocalization. Those are resonance. Resonance leads to charge delocalization. Now we are talking about just resonance. Okay, so we are not talking about any plus M or minus M groups. And we have also mentioned that mesomeric effect and resonance, they have a connection, that all the mesomeric effect are due to resonance, but not all resonance will have a plus M or minus M group. Okay, so all the resonance, it will not have a plus M or minus M group. Resonance is independent of mesomeric effect, but mesomeric effect is dependent on resonance. Mesomeric effect is dependent on resonance. So charge delocalization makes the carbocation more stable, and resonance and hyperconjugation are two phenomena. Resonance and hyperconjugation are two phenomena which leads to charge delocalization. So now when we talk about resonance, so we see that plus I and plus M, we are very much confident in how our different groups, they are going to donate electron and withdraw electron. But in terms of resonance, since we don't have any groups, it is a phenomena. So if we have different types of resonance, then how are these contributing towards stability? So in both of these things, resonance and hyperconjugation, one similarity is that stability will be directly proportional to the number of resonating structures, right? And it is also directly proportional to the number of hyperconjugating structure. And we know that number of hyperconjugation structure, you can just infer that by the number of alpha hydrogen. So write these points. Let me know if I'm very clear about all of this. Yes or no? Tell me.
Yes, sir.
So see, plus I plus M, minus I minus M, and then resonance and hyperconjugation. You have to keep in mind these 6 things. You have to keep in mind these 6 things, or I can say also these 4 things: inductive, mesomeric, resonance, hyperconjugation. So let me know if you're done, guys.
Done, sir.
All of you done?
Yes, sir.
Okay. Now, one very important point, a general rule you can write. So for example, okay, let me give you a question and then we can talk about. So compare the stability. Compare the stability. So you have the question number 1, in which we have to compare the stability between CH3, CH2 positive. Okay, this is structure A, and then we have CH2 positive. Okay, we have CH2 positive. Structure B. So whenever you are comparing, the first thing you have to identify what is same. So whenever there is a comparison, there should be something same. Whenever you compare 2 students, right? So they should be in the same class. Then only you are going to look at the differences. So whenever we have to look at the differences, first of all, you will try to see what is the same here. So you will see that this fragment is same. Okay. So you will never talk about this whenever you are comparing these 2 things. So all your answer should be due to this CH3 group that is attached to the CH2 positive and this benzene ring group that is attached to. So we will be talking about plus I, minus M, plus M, all of these things regarding the ones which I have highlighted in yellow. So whenever you are comparing, you will first of all identify what is same. Sure. Okay, and then compare the different ones. Okay, then compare what is different. So in the A part, you tell me, first of all, tell me, whenever you are going to compare stability of carbocation or any intermediate, you will look out for mesomeric effect. Is there any mesomeric effect in A structure? Tell me, guys. And if you want to look at the resonance or mesomeric effect, so whenever I say mesomeric effect, then you will look, is there any, first of all, is there any resonance here? Because if resonance is not there, there is no question of mesomeric effect, because mesomeric effect is dependent on resonance. So when I'm asking about mesomeric effect, your first thing should be, is there any resonance here? So tell me, guys, can you see any of the conditions of resonance that we have studied till now? Tell me, yes or no? Can you see anything? Yes, Mariam, Reba, Muhammad Sheikh, Sarah. You remember, guys, the conditions for resonance? We have written a few. Oh, Mariam is not here. Yes, Reba, Sarah, Muhammad Sheikh, Rishan. Hey, what happened? Say something. I'm asking, have we learned the conditions for resonance? Yes or no?
Yes, sir.
Please flip your notebooks and answer me. Is there any resonance happening in structure A? Is any one of the condition valid in structure A? Yes, Reba, Sarah. You guys have not written notes, Sarah?
Yes, I've written.
Okay. So you tell me, is there any condition that has been fulfilled or valid in structure A? Yes or no? What about you, Reba? Is there any resonance in structure A, Reba? Reba, if you can't turn the mic on, can you please rejoin or something? Okay. What about you guys? Mohammed Sheikh, you tell me. In structure A, is there any resonance? Umar, why are you always late? Yes, Muhammad Umar.
So actually, I had another tuition.
Another tuition. Okay. When did it end?
So just right now, I was I was telling him that I have another tuition. Please end it quick, but he was like, no. So
Oh, okay. So you don't get everything from Learnivio.
what, sir?
You learn all the subjects from Learnivio only, na? Or somewhere else also.
No, sir. I just have chemistry tuition from Learnivio. All other are from my school.
School teacher.
Yes, sir. One
Is
is
it allowed?
one is my school teacher. The other is a teacher from another school.
Okay. Okay. Yes, Reba, can you turn the mic on now?
Yes, sir.
Yeah. So tell me, is there any condition met in the structure A for resonance? Yes or no?
No.
No. Okay. Then this is the first thing that you will look. Okay. That means in every structure you will look for resonance. First thing that you will look is for resonance. So if resonance is there, that means you can now pivot down to either plus m and minus m. And then you will say, is there any? Then you will find and look up for a group if there is any plus m group or minus m group. Okay. This is the first thing in resonance. Second thing that you will be looking is hyperconjugation. Tell me, is there any hyperconjugation in structure A? So what are the conditions for hyperconjugation? So resonance also, it has some condition, right? A double bond B, single bond C. C has a positive charge, negative charge, lone pair, or a double bond, right? In hyperconjugation, what you have to see, there is only two conditions. Number one condition is sp2 hybridized carbon atom, and the second condition is there should be at least one alpha hydrogen. So tell me, are these two conditions met? Yes or no? In this structure, is there any sp2 hybridized carbon atom? First of all, look at that. अरे what happened guys, why are you so silent? आप लोग पढ़ते नहीं है क्या? Did you guys not revise? Yesterday I have taught hyperconjugation.
Yes, sir.
What yes sir? What do you mean by yes sir?
There's sp2 hybridization there.
sp2 hybridized. Okay, is there any alpha carbon and does that carbon have any hydrogen?
Yes, sir.
Yes. So there is hyperconjugation. So now hyperconjugation, that means you have to look for the number of hyperconjugating structure, and that we can infer by the number of alpha hydrogen. So how many alpha hydrogen are there? 3. Okay. So now when you have got hyperconjugation, thirdly you will look if there is any inductive effect. Okay, so if there is inductive effect, then again you have to classify it whether there is a plus I group or there is a minus I group. Okay, so we have got CS3, and CS3 is what? Plus I group, right? Electron donating group. Yes or no, guys?
Yes, sir.
Okay, now look at the B structure and tell me, is there resonance in B? Is there resonance which involves the positive charge? It should involve the positive charge. Okay, otherwise it has no use. It should involve the positive charge. Is there any resonance?
No.
Yes, tell me. There is no resonance.
No, sir.
Achha. What is the first
Pi
combination for
sigma
resonance?
pi.
Yeah, pi sigma pi is there. No, Reba?
Yes,
Pi
sir.
sigma pi is there. Okay, but again I was saying that it should be involving a positive charge, right? But here we can see now it is also involving. Yes or no? A double bond B, single bond C, and C has a positive charge. There is a resonance, right? Yes or no?
Yes, sir.
Yes.
Okay, now you tell me what is happening in the resonance. This pi bond will move here, correct?
Yes, sir.
Yes or no? And we have also done this resonance, right? We have also done this resonance in the, if you remember, oh my God, seriously guys, you guys don't read. You guys just don't read the notes. देखिए मतलब हम क्या करें बताइए आप लोग को. See, do you see the exact same thing? Yes or no?
Yes, sir.
Yes.
Is the charge delocalized now? Tell me yes or no. Is the charge delocalization? Localization means what? Localization means charge is only on at one place fixed. It is not moving anywhere. Now you see this structure and tell me, is the charge moving? Yes or no?
Yes, sir.
Right. So there is charge delocalization. There is resonance here, right? There is a resonance here. Resonance, and I can say that what is happening, this electrons are moving towards the CH positive. That means it is increasing the electron density, and if it is increasing the electron density at CH2 positive, that means I can say it is a plus M group, right? Now please listen that not always see, you will say sir yahan pe to minus M, CH2 positive is minus M. With respect to what? With respect to benzene, because it is taking electrons from benzene. But if I look at from the respect of CH2 positive will say that benzene is a plus M group. So what did I say? You have to always fix something. So I fixed the CH2. Now I am not going to look at CH2 positive, what it is doing. I'm going to look at the benzene, what it is doing to the CH2 positive. So benzene is giving electrons to CH2 positive, and hence I'm writing plus M. That is with respect to what? With respect to the CH2 positive and looking what is happening to CH2 positive. Okay, so benzene is giving electrons to CH2 positive, and that is why that is plus M. Now, when we have plus M, we don't have to look at anywhere else, and we can just say that B will be more stable, right? B will be more stable than benzene. Okay, B will be more stable than, sorry, B will be more stable than A. Why? Because mesomeric effect or resonance, it has complete delocalization of electrons. And here in this hyperconjugation, there is sometimes some delocalization is there, and at the other times you don't have any delocalization. And also the charge is never delocalized, right? Charge is never delocalized. It is just that H positive gets the charge and sometimes carbon has the charge. So if I compare the order of effects, then there are three things now that we have to compare. Either we have inductive effect, whether it is plus I or minus I. Then we have hyperconjugation. And then we have resonance or mesomeric effect. Hai na? Resonance means, or mesomeric effect is the same thing, mesomeric. Okay, mesomeric effect. So please remember, if I talk about the giving or taking of electrons, then inductive effect, give electrons with spoon. My spoon is bad. Okay, hyperconjugation is going to give you electrons, or it is going to take electrons. You have not studied minus H, it is not there in the syllabus, but still hyperconjugation will give the electrons to carbocation with a mug. Okay, and resonance it is going to give you from a small bucket. Okay, not very large bucket, but with a small bucket. Okay, so the order of the electron, I mean the inductive effect and hyperconjugation resonance, is that hyperconjugation is the least effective, followed by hyperconjugation, and the most effective is resonance. But please see, if we have very high number of hyperconjugation, then it is going to give you more electrons than resonance, and we will look at that case here. Please write this down. Let me know if you're done. I will be spending most of the time with carbocation, because carbocation is something that you need to learn, and you need to just have everything in your mind what is happening. And if you have everything about carbocation in your mind, free radicals will be easy. And carbanions, we don't get carbanions so much so. Okay, in organic chemistry, at least in your standard, we don't get carbanions so much so. But now, if you know about carbocation, you can just reverse everything with carbanion. So please write this down. Let me know if you're done.
Done, sir.
Done, all of you?
Yes.
Okay. Now, so let me talk about things now. Now you have to compare. Okay, now please answer quickly. Enough. Otherwise, I will just answer because I have to complete this, and you guys are not studying, and that is not fair for me. That is not fair to me. So you have to be telling me answers plus and minus and quite quickly now. So compare the stability. CH3 positive, CH3 CH2 positive, CH3 CH2, CH3, and sorry, here we should write CH positive. Then you have CH3, CH3, CH3. There's a positive charge here. So in all of them, here I can see no effect, right? Here I cannot see any effect. In all of them, I can say that there is no resonance. But I have sp2 hybridized carbon atom, and they have alpha carbons. And those alpha carbons, they also have hydrogens. And hence I can say that there is 3 alpha hydrogen here. The number of alpha hydrogen here, it is equal to 6. And the number of alpha hydrogen it is here, which is equal to 9. And hence, as the number of alpha hydrogen increases, the stability will also increase. Right? The one which has higher number of alpha hydrogen will have higher stability. Okay. So this is when you have no resonance. This is when you have no resonance. Now let us look at everything and let us also compare if you have resonance. So let us see what happens if I compare the stability. Now in comparing stability, if I have, let us take the these two things, right? And let us compare this with simple resonance. CH3, CH2, no, CH3, CH2 double bond, CH, CH2 positive. Okay. Then the another structure that we have is CH3, CH, CH3, and here we have a positive charge. Then we have a structure that is this one, CH3, C, CH3, CH3, and here we have a positive charge, and here we have a positive charge. Now, if I compare here, so here we have A, B, and C. So A has resonance, right? A has resonance. And how many resonating structures? There will be 2 resonating structures, okay? 2 resonating structures. We have seen this example when we are dealing with the conditions for resonance. B, it has hyperconjugation where alpha hydrogen is equal to 6. And here the alpha hydrogen was equal to 9. Now we have some kind of messiness here because there are 2 resonating structures, and here the number of alpha hydrogen is very high. Alpha hydrogen is very high, that is 9. And in this case, the alpha hydrogens, since it is very large, 9 alpha hydrogens, it trumps resonance. And the most stable is C in this case, followed by resonance, and then followed by the 6 alpha hydrogens. Okay. So write this down also. This is also important. This is the order of stability. Done, guys?
Done, sir.
Done. Okay. Now, let us write another question. Now, in this we have one benzene ring, okay, and there is CH2 positive, okay. Then we have CH, which is attached to 2 benzene ring, and there is a positive charge on carbon atom. And then we have three benzene rings, and there is a carbon positive charge. Now in all of them, we can say that here also there is plus M, that is resonance. Here also there is plus M, and here also there is plus M. So how we have to compare? We have to now look at the number of resonating sources. In this, we can say that only one benzene group is giving electrons towards the carbocation. Here we can say that there are two benzene rings which are available for the donation of electrons. And in this case, we have three benzene rings which can donate, which can give some of the pi electrons towards the carbocation, right? So in this case, it's quite obvious that the third structure will be most stable, and the first structure will be the least stable, right? So A, B, and C. So in this case, A is the least stable, then we have B, and then we have C. Okay, now we will write a complete generalization of the stability order of carbocations. Done?
Done, sir.
Okay. So something that you need to learn is that if you have the most stable carbocation, the most stable carbocation will be something which has a, okay, one side note, if benzene ring is attached to any group, na, okay, so benzene ring is attached to any R groups. Now in this case, this benzene ring is known as phenyl group. Okay, this is the phenyl group. Okay, the subsequent name for benzene is phenyl. And why you will say why phenyl, not benzyl? Benzyl seems very appropriate, but please remember that phene was the old name of benzene, and from there we have derived the name that is phenyl, and you can't do anything about that. It is very appropriate if it would have been very appropriate if they named it benzyl, but this is phenyl. You can't do anything about that. Okay, it would have been very good if it was benzene. Okay, so this is phenyl because the old name was phene. What is benzyl? There is one more substituent which is known as benzyl. What is benzyl? So benzyl is something if you have the complete benzene ring, you have the complete benzene ring and it is attached to a CH2 group. This CH2 group is attached to something else. Okay, this CH2 group is attached to something else. So this complete thing till CH2, it is known as benzyl. Okay, this is benzyl. Please remember that. This is phenyl. It is shown by pH. It is shown by pH. Now I'm writing the stability order of carbocations, and this is the ultimate stability order that you have to remember. Now, and there will be, this is generalized. Okay, this is generalized. And we will do some specific questions also. So here we have the most stable will be if you have benzene ring, three benzene rings which are attached to carbon and it has a positive charge. This will be most stable, followed by if you have two benzene rings, right? If you have two benzene rings which is attached to a carbon atom and it also has a hydrogen here, right? CH group, a positive charge. Okay, and but this is now followed by if you have three CH3 groups, right? You have three CH3 groups which is attached to a carbon which has a positive charge. That means this is a case of alpha hydrogen, it is equal to 9. Now this alpha hydrogen is, when it is 9, it is even more stable if you have one benzene ring. Okay, so it is even more stable than the one benzene ring, and then it is followed by a simple resonance structure that is CH, 2 double bond, CH single bond, CH2 positive, a simple case for resonance. Now this simple case of resonance is followed by CH3 whole twice, CH positive. In this case, the alpha hydrogen, it is equal to 6, and then it is followed by CH3 CH2, positive. In this case, the alpha hydrogen it is equal to 3. Now we are we are considering everything, right? Resonance, hyperconjugation, and inductive effect. But of simple alkyl, there is no substituent here. Then we have CS3 positive. Okay, so please write this, and you need to learn this. Now, when I say learn this, you have to understand and learn. Okay, to understand and learn. Why is this happening? This part here, it is crucial. Let me know if you're done.
Done, sir.
Okay, right, next. Compare stability. A simple CH2 positive. CH2 positive, and there is a OH group attached here. There's an NO2 group attached. Okay, so in this case, you have to look at the stability. Now, again, what I say is, first of all, you have to see what is common. You have to see what is common in all of these things. So the thing that is common in all of them is that if I just put a hydrogen, because there will be a hydrogen here, right? So I can say that these parts are something which are different. Yes or no? Tell me. And everything else is same, correct? Yes or no?
Yes, sir.
है So now you don't have, now you have focus. Now you have focus. Otherwise you have many things happening. Benzene में 4 3 बॉन्ड है, उसमें तो फिर प्लस m होगा माइनस m होगा, क्या होगा? Now you have these things common. What you need to focus is on hydrogen, OH, NO2, NO2. So again, first drill is that, is there any resonance here? Right? Is there any resonance here? Yes, there can be resonance. Okay, there can be resonance. Okay, in this also, everywhere there is a resonance, and there is similar resonance. What is the effect of this OH group? What is the effect of this OH group? What is the effect of this NO2 group? And what is the effect of this NO2 group? So in this case, first of all, what you have to do, you have to classify them in plus M and minus M. Okay, classify them into plus M and minus M, because this will have no effect. What about OH? It is plus M or minus M, guys? Plus M or minus M? Sorry, plus M or minus M? I could not hear that. OH. No, please look in your notebooks now. Okay, look in your notebooks. Why are you saying? What is the condition for minus M? Mohammed Umar, OH. Tell me, what is the condition for minus M, Umar? You should know the reason. You should know the condition for minus M. Okay, now you guys don't know, so I can go in my pace, right? This will be plus M, this will be minus M, and since your NO2 is at meta position, it will have no effect. It will have no effect, है ना? So now you don't understand. So you start reading. You start reading. No effect as in meta position. We have discussed all of these things. Okay, start reading the notes. Now here we have plus M, that means it is stabilizing. And do we have any plus M other elsewhere? No, we don't have any plus M in any of the other structures. That is why B will be most stable. Now we are going to study. Now we are okay. Now it has no effect, but it will have what? It will have minus I effect, because there is nitrogen. It is attached. Nitrogen is attached. Now let us look at, is there anything which is not doing, which has no effect, right? So we have moved from plus M. Now we want to go to towards the neutral species. So A is neutral because A is neither it is giving electrons nor it is taking electrons. Now we want to go towards who is taking electrons. So I will compare C and D. In C and D, I can say that minus I will be taking minus I will be taking less electron than minus M, because minus M will be taking electrons from bucket, minus I will be taking electrons from spoons, and hence I can say that minus I, since it is taking less electron, it will be more stable, that is D, and then it will be followed by C. Then it will be followed by C. So please write this down. Now plus M and minus M, if you have not learned till now how to identify, then I can't help you. Now you have to start studying. If you don't study, then you can't answer. Okay. And this is the chapter only on the basics. So if you're not answering basics, applications will be in the next chapter, that is hydrocarbon. Write this down. Let me know if you're done.
Done.
Okay. So last comparison here. So in this, all of these cases, I can say that is minus M. This is also minus M. It's also minus M. But here I can say that okay, all of them are effective because it is in ortho position. Here we have both on the ortho position, and here we have in ortho position and also in the para position. And hence I can say that all of these will be effective minus M, because they are not in the meta position, they are in ortho and para position. Next thing is that how many groups are there? So there is only one group. Here we have 2 NO2, and here we have 3 NO2 groups, and that is why A will be most stable, because there is only one bucket which is trying to take electrons. In B we have 2 buckets, and in the C we have 3 buckets. That is why this will be the order for the stability. So write this down. Let me know if you're done. Done, guys? Done or no?
Done.
These are done. Okay. Right, next, that is carbon free radical. So carbon free radical, the structure will be a carbon atom with again 3 bonds, and there is another one more electron. So in this we can say that it is also electron. How many electrons are there? You have 6 from the bonds and 1 as a free radical, so 7 electrons. And since it is 7 electrons, it will be electron poor, because it is less than 8. It is less than 8. Next thing is that the stability is same as carbocation. Okay, what does that mean? So the groups that the effect of groups in carbocation and carbon free radical are same. Okay, so the things that makes carbocation stable are going to make carbon free radical stable. The things which are going to destabilize carbon free radical are also the same one which destabilizes the carbocation. Okay, so the stability is the same. That means stability will be directly proportional to plus I, okay, comma, you can also write plus M. You can write resonance, then you can also write hyperconjugation, and stability will be inversely proportional to minus I, inversely proportional to minus M. Okay, and resonance and hyperconjugation, these are rather phenomena, not groups. Write this about carbon free radical. Let me know if you're done. Done, guys? Yes or no? 4 points.
Done.
Done. Okay. Right, next, carbon ion.
So can you scroll up?
Okay.
Okay, done.
Okay. Now write with me carbon ion. Please write with me, okay? So carbon ion, 3 bonds. Either it will have kind of a pyramidal shape because there is a lone pair of electron here, right? And since there is a lone pair of electrons, I can say that the number of electron is how much? 8 electron. 8 electron, and see, carbon has how many electrons? Carbon has a valence carbon. Okay, how many? First of all, let us see how many proton does it have? How many protons does it have? Tell me, guys, how many protons? Carbon has how many proton? Sorry, what happened? Carbon has how many protons? What is the atomic number of carbon?
6.
6. Okay, so it has 6. Okay, now if I look at this particular carbon atom, so its own electron are 1 2 3 4 1 2 3 4 5, right? So 5 are in the valence shell, and inside that is the core shell, it will have one s2 electron. That will make it 7 electrons, and that will make it, okay, so 1 2 3 4 7 electrons, right? So in total it has 7 electrons, but there are only 6 protons, and hence it will get a negative charge, right? It will get a negative charge. I'm writing 8 electrons in the bonded state. Okay, in the bonded state, 8 electrons. That means it is not, obviously it is not a electronically poor species. 8 electrons and negatively charged. The number of electron is not a problem here. The negative charge is the problem, and hence I can say that stability, if I will take the electrons, it will be happy because I'm taking the negative charge. Okay, so electron withdrawing group stabilizes. Electron withdrawing group stabilizes carbon ion, and electron donating groups. So what I'm doing, I'm giving more electrons, right? So it will be getting destabilized. Destabilizes carbon ion. Okay, that means I can say stability. Stability is what it is, directly proportional to minus I minus M. Okay, minus I minus M, and obviously there will be no hyperconjugation here because we have the steric number is equal to how much? Number of sigma plus lone pair, which will be equal to 3 plus 1, which is equal to 4. So here we have sp3 hybridized carbon atom. It is not sp2, so there is no question of resonance. Sorry, hyperconjugation. Consensus stability is directly, sorry, inversely proportional to plus I. It's also inversely proportional to plus M. Okay, it is also inversely proportional to plus M. So write this down. Let me know if you're done. Then write a question. Write a question. Yes, guys, tell me. I hope you were writing with me.
Done, sir.
Okay, anyone still writing? No?
So what is EDG?
Donating groups, no? Electron donating groups.
And WG?
Withdrawing groups.
Okay.
Okay. No. So here, if you're going to write the stability, let us just write some questions. So if I'm going to compare CS3 negative and CS3 negative, and then we have CH3, sorry, CH, yeah, CS3 CH2 negative. Then we have CH3 CH CH3 negative, and then we have CH3 C CH3 CH3 negative. So in all of these cases, there is no resonance, so there is no hyperconjugation. There is no resonance, and that is why there is no mesomeric effect. There is no hyperconjugation because we don't have sp2. So all we are left with is inductive effect. Here there will be no inductive effect. Here the CS3 is a electron donating groups, and this is a plus I effect. Here we have two CS3. That means there is plus I and plus I, 2 plus I. Here also we have plus I, and there is another plus I, right? So in this case, we can see that if I have these four structures, namely A, B, C, and D, then in all of them, I can say that here we have 3 plus I groups. So we are giving more and more electrons. We are making it more and more negative. And if the charge is increasing, then we are destabilizing it. Hence, A is the most stable here. B is the next, C is the next, and then we have D, which is the least stable. D is the least stable. Write this down. Done, guys?
Done, sir.
Okay. This side, let me give you two questions here. So in one of the cases, we have CH3, CH2 positive. Okay. The next case, we have CH2 double bond CH positive, and in the next case, we have CH triple bond C positive. Please remember, this is a carbocation. Now, if I look at these groups, now CH3, CH2, CH, the only thing that is different from within all of these is the hybridization. So the hybridization here, it is sp3, here it is sp2, here it is sp. Now I can see that there is an increase in the s character, percentage s character, right? Because here we have only here the s. Okay, if I say percentage s character, that means there is a lowering of p, and that is why the percentage of s is increasing. So if the percentage of s character is increasing, that means the electrons will be very near to the protons. The electrons will be very near to the nucleus because they are in the s subshell, the bonded electrons, and that is why sp carbon, they can easily pull the electrons, right? They can easily pull the electrons, and hence what will happen, this will be most stable, followed by sp2 and followed by sp. And also we know that the electronegativity, if I compare now, so the electronegativity of, if I compare the electronegativity, sp is most electronegative, followed by sp2, and then we have sp3. Okay, so this is the electronegativity order of carbons if we have different hybridization. Okay, next thing is that what will be the effect of same groups if we have a carbanion? We have a carbanion CH3 single bond CH2 negative. We compare this with CH2 double bond CH negative, and if I have CH triple bond carbon negative. Now in this case, all of these are pulling electrons, right? This will be pulling electrons. If they are pulling electrons, then what will happen? What will happen? This is more electronegative. It will pull a bit more than the sp3, and it is most electronegative. That means it will be pulling all the electrons from the from the negative charge. Hence, they are what? They are stabilizing the negative charge. So this will be most stable. followed by the sp2, followed by the sp3. Okay, so write these two. Write these 2 points. And let me know if you're done.
Done, sir.
Okay, so let us write now. What will happen if I compare CH2 negative and CH3 negative? So in this case, I can say that there is a resonance. What can happen? The negative charge can go here and it can delocalize, right? So if there is delocalization, then obviously it is going to be more stable. So if you have a resonance effect, then that means you are going to stabilize the carbon ion, and hence you can write the ultimate generalized order in which you have pH thrice, that means pH whole thrice, carbon negative, it will be most stable, followed by pH twice, CH negative, this will be next to stability, followed by, if you just have one pH and you have CH2 negative, this will be next. This will be followed by a simple case of resonance, that is CH2 double bond, CH single bond, CH2 negative. This will be followed by a simple CH3 negative, and then you will have CH3, CH2 negative, followed by CH3, CH3 has a negative charge, and then the least stable of the carbon ions will be a tertiary carbon, CH3, CH3 and CH3 with a negative charge here. Okay, so write this down. Let me know if you're done. Done, guys?
Done, sir.
Okay, all of you done? Yes or no?
Done, sir.
Okay.